Greetings from NASA headquarters, the Office of Aeronautics and Space Technology. We've heard some discussion for many years of power beaming from space to the Earth for various purposes, or perhaps from space to power satellites or the surface of the moon. Today I'm going to talk to you about a different variation on that theme. Basically, we feel that we need to learn to walk before we can run, and so I'm going to discuss the possibility of beaming power from the surface of the Earth to space. We've had a program going on now for the better part of 2 years at NASA to explore the critical technologies that might make this feasible and to look at the systems concepts that may make it desirable to do this. We have called the program Project SELENE, which means Space Laser Electric Energy. Next slide. SELENE has the objective of developing and demonstrating technology items. In other words, we're looking for the high leverage technologies that may make this economical and feasible. We want to pursue low-cost, reliable space power and propulsion for spacecraft based on the principle of photovoltaic conversion of laser light to electricity in space. Next slide. This would be accomplished by having 4 sites spread around the Earth, or perhaps I should say at least 4 sites, that would look something like this. You would have a free electron laser of a new type situated in the building in the background, delivering high power to a new type of telescope or beam expander, which then transmits the power to space. A very important and critical element in this is down here in the bottom of the well in bedrock, a wavefront sensor which senses all of the disturbances in the atmosphere and enables us to correct for those disturbances so that the beam arrives at the target in space completely corrected for the atmosphere. This is a very safe system because it depends on a beacon at the receiver to deliver a signal which will attract the beam from the ground. In other words, we can't transmit the power from the ground to space without having the beacon signal coming down, and this ensures that it goes exactly where we want it to go. There are many other inherent safety factors that we'll perhaps describe later. The next slide. There are many high-power space applications, among them electric propulsion, which people are familiar with in the context of solar propulsion. We're trying to do things faster, cheaper, quicker than you can do with solar. Secondly, power to the lunar base, the fructifying principle for developing the moon in a large way. Thirdly, life support for large manned space stations, where power is a critical factor. The fourth is industrial processing, and that equates even to production of oxygen on the surface of the moon. 1 megawatt of power delivered to the moon for 1 year continuously would equate to 600 tons of oxygen. We are already familiar with what you can do with radar in space. High-power radars can serve many purposes, also direct broadcast television transmission and remote sensing. Next slide. Now, why are we talking lasers instead of microwaves? People have heard about microwave transmission for years. The critical difference is in the wavelength. The wavelength of the lasers that we're talking about would be 1 micrometer, 1 micron, in the near infrared. This is a factor of 10,000 times shorter than the typical microwave frequencies that would be used to transmit power. And what that means is that the physics of the system will enable you to deliver a lot of power from a much smaller transmitter to a much smaller receiver than you can with microwaves. Basically, if we focus at 1 micron wavelength here and look at geostationary range, the diameter of the transmitter on the ground will be on the order of 12 meters, and it will deliver all of the power to a spot no more than 10 meters in diameter at geo. So this means that we could power very high power satellites or orbital transfer vehicles to that altitude. Similarly, if we follow that same 1 micron line out to the distance of the moon, you find that your 12-meter diameter transmitter on the Earth can deliver all of the power to a spot about 80 meters in diameter on the moon. Since the moon keeps one face to the Earth all the time and librates only 7 degrees, this means that the power would be available throughout the lunar day and the lunar night without any abatement. The next slide shows you why lasers are very advantageous over solar. The efficiency of a solar cell, as on the space station Freedom, is about 13.5%, and this equates to about 9 kilowatts from an array of 50 square meters. If we went to advanced solar cells like gallium arsenide, we could achieve an efficiency as high as 22.5% or 15 kilowatts from a 50 square meter array. If we instead used a laser providing the same illumination as the sun, but using the same gallium arsenide, now the efficiency jumps up to 58%. Why is that? Well, it's because the wavelength of the laser light can be matched to the band gap of the material so that the efficiency of transfer of energy is much greater. You produce much less waste heat in the cells. Also, since we have an optical system that can concentrate the beam, we don't have to settle for one sun's power. Instead, we can go to as much as 5 suns, which will heat the array to a higher temperature. The overall efficiency may drop off a little bit, but you see now that we're up to 8 times the equivalent power that we would get from solar cells exposed to the sun in the usual way. So we get 120 kilowatts from a 50 square meter array instead of 9 kilowatts as originally stated. So overall, the laser beam power is a factor of 8 or 10 times more efficient than solar power. Now, this can really have a big payoff in space transportation. We all know that it costs a lot to get from the surface of the Earth to low orbit, somewhere in the range at present from $12,000 to $70,000 per pound of material. If we had a tugboat such as the one shown here, we could potentially move payloads from low Earth orbit up to geostationary orbit or on to low lunar orbit much more economically than presently possible. The concept you see here, we have a 20-meter diameter photovoltaic array which is tuned to the laser wavelength, is receiving the energy and passing it to the plasma engines here, which are able to propel this payload pretty fast. It can get from low Earth orbit up to geostationary orbit in about 30 days or less with a payload of about 2,500 kilograms. The trip onto the moon doesn't take very much longer because you've done most of your work by the time you get to geo. Next slide. You see that the real boon here comes from the fact that you're not having to carry along a huge solar array and the associated PMAD, nor are you having to carry along a nuclear reactor. Instead, you have an array which is matched to the needs of the engine so that you deliver pulsed radiation to the array which powers the engine directly, and the pulses are tailored so that they match the impedance of the plasma system so that you eliminate a great deal of the weight of the propulsion system. And this comes back, of course, favorably in terms of the amount of payload that you can carry. Next slide. We're looking at some particularly important electrodeless thrusters with long lifetime. The bottom line down here with the red numbers, you see that the kilograms per kilowatt is on the order of half a kilogram per kilowatt as compared with 4 to 8 for some of the other electrical engines. The thrust is higher in the range of 1 to 20 newtons, and the lifetime is long, greater than 3 years. So this means that we can enable better performance with very high efficiency transport using this method of beaming laser power. This comes home in the form of great cost benefits. The gray area at the top of this chart is the cost of delivering payloads from the Earth to geostationary orbit using conventional chemical systems. And you see that they come in somewhere around $60,000, $55,000 per kilogram minimum. Now, a solar electric system does pretty well if you're not in any particular hurry about how quickly you do things. If you were delivering 2,500 kilograms, it would take you on the order of 150 days or so to perform that mission. The laser system does even better, factor of 2 better cost-wise even than solar, and it can do the job quickly, like 30 days as we've said. And therefore, we're talking about a very large factor, at least a factor of 4 or more, less expensive per kilogram of payload, raising it from the surface of the Earth to high orbit. Next slide. It's interesting for the technical students in the audience to consider the trade-offs that you have in such a system. Chemical rockets, the mass flow rate per unit thrust is high. Although you do the job quickly, you have to have a very large amount of fuel, and the payload fraction is small, typically 2 to 4% maximum. On the other hand, if you use old-fashioned electric engines, ion engines, the power per unit thrust is large, and even though you may have very high specific impulse, up here 10,000 or greater, it's still expensive in terms of power. So there's a minimum where you trade off the specific impulse against the power available, and we are operating just in the middle of that regime with the laser propulsion scheme. Next slide. Now let's consider the lunar base application. Here the astronaut is showing you an array of laser photovoltaic cells that he's unrolling here. And if you look off the right side of the screen in the red spot over there, you have a large number of those arrays set up so that they are receiving the laser power that's beamed from the Earth. There would be a beacon off to the left of the screen about 2.5 kilometers out that would be providing the signal back on the Earth with the proper lead ahead for the speed of light, so that you will ensure that the laser radiation lands in the middle of your array here. Now we can transmit megawatts of power all the way to the moon with this very low weight array to receive the power. This is ample power to provide major soil processing and soil moving capability on the moon. As I previously said, we can generate major amounts of oxygen to supply the shuttlecraft that you see sitting there in the background to go up to low lunar orbit and receive the payloads that have been brought by the laser-propelled craft from the Earth. So we can complete the logistics link all the way to the moon, partially with oxygen generated in situ on the surface. Of course, we also get nitrogen and we get hydrogen from the lunar soil. I'm told that we get on the order of 600 tons of oxygen per megawatt of power per year, about 50 tons of nitrogen, about 10 tons of hydrogen from the beamed power. So power is everything in terms of availability of capabilities on the moon. I'm not advocating that we deliver all of the moon's power forever this way, but that we use it as a way of getting a leg up to initiate major development of the moon, to put in place the resources that make it a permanent self-sustaining colony. Next slide. Looking at the comparison at the level of 550 kilowatts, of the different types of power systems. Here we have the amount of mass that needs to be delivered to the moon in metric tons, 30, 60, 90, versus three options. The laser beamed power is very small down here around 20 metric tons. The nuclear comes in here at around 80, and solar photovoltaic with regenerative fuel cells way up above 130. So there's a vast difference in the cost of delivering these systems to the moon. We think it could really be a very important catalytic technology for developing the moon. What we would deliver to the moon is, this is supposed to be the Earth at the top. There's a Gaussian distribution of power that's impinging on the moon. You find that you'll get about 65% of that power within a spot 50 meters in diameter, and you'll get 85% of the power to a spot 80 meters in diameter. Now let's look at the technologies that support this, and this is actually the principal focus of what's ongoing at NASA now. Next slide. The free electron laser was invented in 1975 and has gone through several phases of development so far, several generations. It's very simple in concept. It's rather like a relativistic traveling wave tube. You have some sort of accelerator which delivers relativistic electrons through a row of alternating magnets, north-south, south-north, north-south. If you launch a light wave that's co-traveling with those electrons, as the electrons are accelerated back and forth so that they try to zig and zag in the magnetic field, the electric vector of the electrons pushes on the light wave, and you've built yourself an amplifier. So you can choose whatever wavelength you want by choosing the energy of the electron beam going through this system. This, in the equation over here, the factor of gamma squared is the relativistic energy, and you see that it's in the denominator, and so that if you double the energy, you go to 4 times shorter wavelength. Turns out that to operate at 1 micron in the near infrared, you need about 150 MeV, million electron volts. So we're looking at how do you build a free electron laser that's reliable and can operate for long periods of time safely and reliably. We also have to look at the question of how do you build an optical system that's cost-effective and reliable, and how do you overcome the atmospheric effects that tend to degenerate the quality of the beam. Next slide. Therefore, we have a rather elaborate program going on at several different NASA centers. The program is being managed out of Marshall Space Flight Center in Huntsville, and the free electron laser development work is going on there. Also, certain vital components of the optical system, the small components, are being built there in collaboration with the Lawrence Livermore National Lab. The principal optical work and the design supporting it is being done at the NASA Jet Propulsion Laboratory, and the photovoltaic work looking at both power and propulsion is being done at the NASA Lewis Research Center in Cleveland. Next slide. Now, we're not starting from zero. In fact, we're starting from a very long and large research base that's been going on for 15, 20 years. Here you see an extremely large accelerator at the Lawrence Livermore National Lab. This accelerator is sort of the grandfather of the machine that we're now trying to build, but it gives you some feeling for the magnitude of the technologies that are required. This is a high current accelerator that produces pulses at about 1,000 per second. We're looking at essentially the same current, but at about 10,000 times per second to achieve the performance that we need. The next slide. Those electron pulses pass through a Wiggler magnet, such as you saw in the previous slide for the free electron laser. This is the Wiggler magnet, and you can see that it's a rather complicated device itself with electromagnets that enable you to fine-tune the strength of the field. This thing is about 25 meters long. Next slide. We're looking at much more recent technology and much more elegant, I think. We are repackaging the accelerator components into nice packages like this. This box is about 1.5 meters long and about 1 meter wide. And you see in there the pulse-forming network and the accelerator module. It would take about 150 of these boxes to build the complete accelerator that we're talking about. But the really encouraging thing is that they are very reliable and they're coming in at very low cost. And therefore, we view this as a very important key to the practicality of the whole scheme, since it implies that we can build the entire accelerator and free electron laser for under $200 million. Next. Now, sight is very critical for lasers because you can't transmit through thick clouds. You can probably get through cirrus clouds okay, but you don't want to be in areas where it rains a lot. That means in the 48 states of the United States that we definitely have to be in the Southwest, perhaps in New Mexico at White Sands or in California at China Lake, which has about 275 days a year of very acceptable weather. Now, it turns out, you may remember at the beginning I said that we were looking at having 4 different laser sites spread more or less equally around the world. You would choose equally good sites at all 4 locations. Then you look at the joint probability that the radiation can be sent from one site or the other to a point in space. It's very high, up around 99%. So we would have very small outage time for such a system because even if one site were clouded out, the other 3 would likely be available the other 18 hours of the day. Next slide. Second thing you have to think about for the atmosphere is the attenuation as a function of zenith angle. Now, zenith angle is the angle from the point straight up. That's 0 degrees, 60 degrees, 70 degrees. It turns out that at 60 degrees the secant equals 2, and therefore you're looking through essentially 2 atmospheres, and at 70 degrees you would be looking through 3 atmospheres. And so your situation gets much more pathological very quickly as you go to large zenith angles. And you can see that if we, from this chart, if we were operating at short wavelengths, we would take a great deal of punishment from the atmosphere in a hurry as we went from straight up. Now, if you'll focus on 1 micron at the bottom of the chart, you'll notice that there's a very good window in the atmosphere coming up. And it turns out that even at 70 degrees, we can expect to get about 75% of the beam through the atmosphere to space. So that's quite acceptable. You say, why don't we go to the longer wavelengths out around 2 microns? Well, we could do that, but we take punishment in several ways. First of all, the optics, both the transmitter and the receiver, would have to be twice as big. And secondly, the photovoltaic efficiency falls off rather dramatically as you go longer than 1 micron. So we have to look at an optimization of all the critical components of the system, the transmitter, the receiver, the photovoltaics, the ability to build the laser that can run efficiently. And all of these things seem to optimize around 1 micron wavelength as we presently understand it. Next slide. The other thing that's tremendously important about the atmosphere is the scale of the disturbances that you have to correct. The disturbances to a beam propagating through the atmosphere are rather much like what you see on the bottom of a swimming pool. If you have been in a swimming pool on a clear day when the sun was projecting on the bottom of the pool, you know the rippling pattern of bright and dark patches. Well, it's a very similar phenomenon to what you would find in the propagation of any beam through the atmosphere. And therefore, you have to have an adaptive optic system that can resolve those disturbances both in time and in space in order to correct them and to make it possible to reconstruct the beam. Basically, as I said, there is a beacon signal coming down from space that provides you the photons that you need to analyze what the atmosphere is doing. After you've done that, you adjust the adaptive optics so that you pre-bias the beam that you're transmitting out so that it goes back along the same path that you've just measured, and the waves that emerge from the atmosphere and go off into space then add back together in such a way that it forms up to an essentially perfect beam. At the 1 micron wavelength we're looking at, what this chart is telling us is that straight up the scale of those disturbances may be around 12 or 13 centimeters. However, as we go over to 70-degree zenith angle, it gets down to about 4 centimeters. And so this means that whatever we do to correct for the atmospheric disturbances, we have to do it on a scale of 4 centimeters. Now, if we're using a very large transmitter, 12 meters in diameter, that means hundreds of thousands of zones, about 200,000 to be exact, that we have to correct for. And this is a factor of 100 larger than any adaptive optics that's been previously demonstrated. And so we had to find a better and cheaper and more reliable way of doing it. And that's where we're concentrating the second major technology development effort at NASA. First of all, it is important to realize that work has already been done demonstrating feasibility. This work here was done by the Air Force and the Strategic Defense Initiative organization at Maui. And as you see, it's a very complicated looking system, but it did the job. Now, what we want to do is take this and make it into something that would be industrial quality. This is real data taken from the so-called LACE satellite in space in November of 1990. LACE was a calibrated target that shows the quality of the beam that's going up. With the adaptive optics turned off, you got essentially nothing, and with the adaptive optics on, you see that you get an essentially perfect beam. Now we intend to do the same thing for our other approach. Next slide. We're undertaking this in a very interesting way. It's been known for 2 decades that you can build large, precise radio telescopes like this one. This happens to be 12 meters in diameter at the National Radio Astronomy Observatory facility in Arizona. This can be built very inexpensively. What you see there is under $5 million, whereas you know the Keck optical telescope that's now being built on Maui is a $100 million device. What we asked ourselves is whether we could get clever about how to build these large systems and make them adaptive at the same time. Now the next slide shows what we endeavored to do. The effort at Marshall is to build small segments like these, which can be mass-produced and populate the reflector as you see, so that it will perform all of the adaptive optics functions. These are little machines, each one with its own microprocessor, each one capable of doing the corrections that are needed in parallel, so it's a parallel processing system. It's really a Silicon Valley breakthrough for optics. Next slide. And I don't have time to elaborate on all the details that we've gone into to simplify large optical systems, but everything that we've done has been done in such a way that we've reduced cost and reduced complexity. Next slide. I would like to explain to you the details of how the system works. Suffice it to say that these smart little segments receive a beam from space, measure all of the perturbations, and generate 3 piston commands on each one. 3 points determine a plane, and that enables you to put the segments where they need to be to make the necessary correction. Next slide. Now you put it all together, what do you get? The zenith angle effect shows here, you see that you lose as you go to the larger angles, but nevertheless, when we add up the error budgets and the loss budgets associated with doing this, we see that even in the most pathological situation, we can get about 30% of the power where we want it to be, and in a lot of cases, we can get more than 50% there. Next slide. So what it comes down to then is that for 110 megawatts of power that goes into the Earth site, we will be able to deliver about 2 megawatts to the receiver in space with very high reliability, taking into account all of the losses along the way, the efficiency of the laser, which is about 10%, and the atmospheric effects that I've described. This may not sound like it's terribly efficient, 2% or so overall, but when you think about how it implements things and how all of the vital equipment is on the ground in a hands-on environment, you don't have to launch it into space, then you begin to realize just how important this can be. It greatly simplifies the systems in space at the expense of clever things that you're doing on the ground. Next slide. We've looked in many system studies at the market and the details of the various missions this can perform, and we find that about 3/4 of them would benefit from this. In fact, the bottom line is that looking at the cost benefits, we believe that this can pay for itself very rapidly and that it'll have about a factor of 10 advantage over any other rival system. So I'm going to have to stop there. I would like to provide a lot more information for you, but I hope this has at least tweaked your thinking about new ways of doing things, and hopefully as we move forward into this decade, we'll have some very substantial and robust demonstrations of capability. We have our first tests are hopefully going to be in 1995 with some initial operating capabilities in 1998. Thank you very much.